This is great. We're here today. Welcome in Dr. Woodbury and the map we never got. We're excited to be here today. I'm Dan G. I'm the Educational Outreach Director. And we have our special guest with us today, Dr. Woodbury. And you want to take it away?
We're going to talk about the book I have written and publishing. These are our review copies, but it's called The Map We Never Got. And it's all about why the science you learned as a kid was wrong and what our kids deserve instead. And so it's really just a primer. The first half of the book goes over a number of major misconceptions that students carry all the way into adulthood. And then the second half of the book talks about how we got here. So this is the research piece. So the first part is the map that we never got, and the second part is the research behind that map. But what we wanted to do today was talk a little bit about why I wrote this book and give some background. And in fact, we're going to spend a number of weeks talking about this. It's kind of a complex problem that I didn't recognize when I first started writing science books. What was it, 30 years ago or so? So I didn't understand initially when I started writing science textbooks why there was such a problem with particularly elementary, but also middle school science. And I want to just show you this graph here, if you can see it. So this is what actually got me interested in trying to unpack why do students fail in high school and in college? And in my own experience, I went to college, I had made straight A's in high school, I was a good student, and I promptly flunked my first chemistry test. And one of the things it did was shatter my confidence. And it took me years to build that confidence back up. And later, when I started having my own kids, I wanted good science books for them. And I started looking at the elementary and middle school books. And I was like, there's no science in these books. What happened to the science? The content in these books isn't going to prepare my students, my kids, or anybody else's students for the high school and college level science that I now knew I knew, right? So I got interested in unpacking this problem. And it was one of those situations where you think it's just going to be this little problem, but as you dig deeper and deeper, it just turns into this bigger and bigger problem. It is truly a Gordian knot in a sense that it's all intertwined. Science education is intertwined with cognitive science, which is intertwined with a number of our major science organizations and teacher organizations, that's then interconnected to funding agencies, that's interconnected to standards, writing the NGSS standards, for example. So it's this very complex, mixed, really tightly knotted problem. And so we're going to dive in over the next couple of weeks. We're going to dive in and we're going to take a very closer look at this. But one of the things that got me interested in studying this problem is these are AEP science scores. So I started looking at the testing for students. And most of the time when you see these test scores recorded, tally every grade level separately. But I put the 3 grade levels together. This is grade 4. This is grade 8, and this is things I noticed right away was that you have 4 and 8 doing okay. Kids really love science in the elementary grades. You can see their scores are higher. And in fact, there's some other assessments that talk about how kids are really excited about science in the elementary grades. And then you get to, it's not bad for the most part. But then you get to high school. High school is the red here. And you can see this massive dip in proficiency. So this is NAEP science scores, and this is percent of student proficiency. And you can see our proficiencies are still relatively low. They're in the 30s, right? They're not in the 50s, 60s, or 80s. Since 2005 that these scores were recorded, you get this massive drop, dip when they get to high school. And it's consistent across all the grade levels. Notice in 2024, they didn't actually do the NAEP test for high school or for grade 4. So I can only report the grade 8, but you can see grade 8 is 4% points down from 2019. So we continue to drop in our students' in science. And that's independent of all of the STEM products that we've been creating over the years, all of the revisions to our science standards, all of the new curriculum materials that have come out, right? It doesn't seem to matter what we do. Students still score low, and in high school, they drop even more significantly. And if you can see this chart up here, this has a huge impact on how we perform as a country. On patents that we participate in or we submit has gone down 32.7%, 2019 to 2023. So you can see China has overtaken us. So this quote up here by Dr. Nutt, this is her State of the Science address in 2024. She basically says the US science is perceived to be and is losing the race for global STEM leadership. So we've already lost the race for global STEM leadership. So this has a huge impact on as a country and as a global science and technology powerhouse. We're no longer the first country to put the men on the moon. I mean, we're just no longer in that. And you can, anyway, our R&D expenditures we have a decline of U.S. share of global R&D expenditures. So we're not doing this is 1980 and this is 2025. So we've decreased the number of even lower.
Oh, yeah.
And then now we've gone from 8th place in our overall innovation index, from 6th place to 8th place. So we just keep declining. Just, some crazy lady ranting about middle school science education. There's a root cause to why this is happening. And that's what we're going to unpack. And it plays you can see it clearly, and it plays this huge role in the number of even in the number of students that pursue STEM careers. It's just tanking. And so we want to unpack that today.
Absolutely.
For you guys. What we've been working on, and that's part of the reason why I wrote this book. This is our review copy. We've out. Anybody wants to be a reviewer, just email us. And we'll send you a copy. Well, actually, what we can do is we can send you a review copy. And if you send it back to us, comments, we'll send you a review copy and a red pin. And if you email us and we have enough review copies left, we'll send you one. And then if you to us, we'll give you a free copy of the final version. How does that sound?
That sounds pretty good.
Yeah, that'd be fun.
Yep.
So this is our review copy. We've got some tweaks but the book is almost ready for prime time. But again, the book is a primer on why are we here. So let's switch gears a little bit and dive in. Dan, why don't you talk a little bit about the Project 2021? This is kind of where it all got started, right? So tell our viewers, well, how do you know about this? What happened? You dove into this research years ago?
2 years ago. So now, yep. We just finished a year-long after-school program where we taught.
Yeah, it was fun. It was a lot of work. Huge gains for the kids.
Yeah.
Huge gains for the students.
And so we finished, and then in the beginning of June, we went to a superintendent conference.
Right, we went to a superintendent conference trying to share our program.
Yep, we put the backdrop, we bring our books and all our wares, and we stand there, smile, and
well, and we tried to engage them in this Adams First program that I've spent 30 years developing, trying to get them to see the new, program. And what we got as feedback was, well, if it's not evidence-based or NGSS aligned, you can't actually buy it, right? In some states.
Absolutely. Like this particular state, the individual high up in the totem pole within a particular school district said, we can only buy non-standards aligned material if it's a one-off. In a textbook, it's hard to justify a hardcover textbook as a one-off in a school.
Right. Well, and even one of the superintendents came up and said, even the supplementary materials, which we'd been category, not, the gen ed material that the regular classroom uses, but any kind of supplementary material. He was like, we can't even buy, we have the NGSS requirements.
Yep.
And then they threw around this term quality instructional material.
Okay, yeah.
Right?
Well, I mean, that's how everybody classifies all the instructional material and the curriculum material that's present in the classroom today. And they co-opt this term called high quality instructional material, and then it's supposed to mean evidence-based. And so they took that and they created a organization to then go and do reports on curriculum to see if it aligns to what they want you to align to. And
so this is Ed Reports.
So, yep.
Right. And Reports is kind of the gatekeeper for any material. If it needs to align to NGSS, and it needs to be counted as high quality instructional material. And many school districts, right, have these requirements.
Oh yeah, like you can't sell a product that doesn't align to Ed Reports. Right. In like all of these different states. I've looked at I've tried to apply to all these states. I've applied to many of these places.
I submitted a lot of RFPs. A lot of the requirements were, we don't align to NGSS, and we're going to tell you why. And wouldn't be considered a high quality instructional material, but the evidence-based piece of it is an interesting Sue.
Right, yeah. I mean, it's so funny that they sit there and tell us, they stare us in the eye and say, we can't buy your product because it's, and so that summer, that fueled us. And we just started to, because we couldn't find any of the evidence. So then we started to read research papers.
Well, conference, and we went, well, what is this? What does this really mean, this high quality instructional material? What do they mean by evidence?
Right.
So, I had gotten my master's in instructional curriculum and instructional design. And so I had some of the references handy, and I knew many books that, those in the field use. And we just did a deep dive, we bought of science, which one it was?
Those 2020 Handbook of Science Education.
Yeah, Handbook of Science Education, those big thick books. We bought that.
Yep.
We dove in and we started doing the research, and we had the whole floor full of papers, remember?
Yeah, I had them chronologically ordered, and there were stacks for every year. In 1970, and then 80, and then 85, and all the way up every year. And my goal was how can I find all of the research papers that are relevant to what these people are talking about superintendent's conference.
Well, yeah. And me personally, I was thinking, I have spent 30 years developing this program. And I was thinking, well, maybe I'm missing, maybe there is a body of evidence that I just am not aware of. I looked for evidence when I was, like I said, doing my master's program a few years ago, and I didn't find any, but that doesn't exist, right? I mean, so I actually called some folks that on the chain, they published some papers, and I called them up on evidence. Where's this, what's the evidence for the evidence-based high quality instructional materials that are now required for students, for schools? Yep. And then that's, what gets delivered.
It's mandated by the Department of Education.
Right.
That they have to, like your kids have to learn this type of science when they go to public school in pretty much every state that's out there.
Right. So that's what we wanted to dive into. And so what we discovered, so why don't we talk a little bit about this? This is Project 2061.
Yep.
So you did most of the research on this piece. So why don't you talk a little bit about how is it, the Project 2061 is basically the starting point in essence, right? There was a little bit of work before that. This is what shapes the NGSS, ultimately shapes the NGSS. So let's walk through that a little bit.
Perfect. So the meant for American Association of Science,
right,
I think is what it's called. Well, the American Association, but their directors or people in charge, 1985, decided that they wanted to standards
for assessment, primarily, right? It was initially around assessment.
Well, I think assessment came later with No Child and George W. Bush. In 2002.
But you're saying they were like, well, let's do a more concrete set of standards, and the reason behind that was because most of the states had their own different varied standards.
I think so. I think that their motivation back in the day was to help teachers and educators be able to teach science, even though they weren't.
Yeah, then that's a fair goal. In fact, my Real Science for Kids program is all about that too. I wrote my program for the non-science homeschool educator initially,
right?
And we applied it, and now we're available to schools. But that was, I had the same goal. I wanted non-science individuals to teach science to their kids.
Yeah. So this 1985 project, they call it Project 20, and that was to correspond with Halley's Comet when it comes back around by Earth. it was going to be in year 2061. And so that was their moniker. That was how they were given. That was the fuel. They were driven, right? There was a couple education researchers who were asking some science type questions back in 89, 85. They're trying to analyze kids think. And they ultimately connected with Project 2061. Those same published a framework, and then they published these standards. And the problem that they had is that they felt like they were really narrow, wide.
Right.
Like we were
shallow
giving,
and
yeah,
broad.
like we had all this info, but it never really went deep. Like what?
So when did this get published? Do you remember?
Published this atlas. So now these people have been working on this for 20 years.
Right. So this was published when?
Okay, so they kept going, and in 2001, the National Science Foundation funded $6 million, $1.5 million per year for 4 years, for them to publish Atlas 1 and Atlas 2.
Right. So this is states of matter here. So it's a big description of what is state of matter. And then if you flip it over to this side, you see these grade level bands. This is K2, this is 3.5, this is 6.8, and this is 9.12. And the idea is, and it's not a bad idea overall, is that you introduce some foundational content in K2. Then you build these arrows point to different aspects in grades 3-5 that connect. And then these point to different aspects or different topics in grade 1. So it's a nice map of how you can start from what they consider basic building blocks to more advanced learning.
Right.
So that's them. And then every one of these, so why don't you hold that slide? So this is states of matter. The one before is conservation of matter. So you can see it has the same sequencing. If I go back again, this is where atoms and molecules start. Yep. So these are the 3 pages about atoms and molecules. K2, of matter, states of, chemical rate. And then this one moves to physics, laws of motion. So let's just states of, on the matter.
Well, so it keeps going. I have this map now. It's funded. They built it off of all the materials that they have. And this is what they want to segment these things. And this is very similar to how the NGSS standards are aligned.
So this shaped, it's not identical to the standards, but this document shaped standards, right? It shaped
their views. It shaped the learning progression. I'll tell you about that in a second.
Yeah.
It shaped everything. It literally is a keystone that then got.
We weren't involved in this. So basically we had to piece it together based off on all the research. We just kept pulling papers. And then this would be referenced. And we would look at several of, the LEAPS conference book and
all of them.
Science education, and would refer to this. And so we basically pieced this together that, okay, this document here,
this was so they created, so in 2004, this is finished.
Right. Okay. And 4. This one was
almost finished. Okay. It's publication stage.
Right.
Right. They're ready to go.
Yes.
So the National Academy of they do at this time.
2 cameras running. One of them keeps going a little AWOL.
Yeah, keeps going AWOL.
So this is the 2004.
This is 2004. Right. The National Academy of Science has, they get the team that was in the 80s. What is it? It's energy for the one in 89.
Well, they did energy, did evolution.
Now we're here. It's 2004. This book is almost finished. Those same people that were doing those studies, they're all friends.
And I think it's important to note here, they're not scientists. They're cognitive psychologists.
Right.
So there's almost no scientists, practicing scientists that we could tell was involved much. Most of this is done by psychologists. And educators.
Right. Yep. So 2004, they come to this team and say, I need you to create an assessment, a way to assess this atlas.
Right. There you go.
That's what they did.
Okay.
And then that's where, out of that, they published in measurement the first one in 2004. And then they published the real paper in 2006.
Yeah.
And that was the learning progression for atomic and molecular theory following outdated
Right. And
map.
we got that paper and we dissected. It's a learning progression. So learning progressions also became something that was fashionable to talk about. So a learning progression, the idea is that it's a map, right? It's a map of how students should learn subject. And so Carol Smith and her team put together the learning progression for atomic molecular theory. And if you read paper, it's actually good paper. I mean, I don't agree with the progression, and I'll talk about that in a minute. But the paper, they talk about the learning progression being based off of conjecture and hypothetical. And they also say that, so if you see up here, I know you can't really see it, but this is the 9, 10, 12 grade band.
Yep.
And this is where all of the real atomic molecular discussed.
Yeah, about atoms.
More about atoms than these lower grades. It starts talking about atoms in 6 to 8. There's no atoms here, and we're going to talk a little bit more in detail about what's down here. But one of the things that Carol Smith notes in her 2006 paper is that most students don't get to this grade band. They don't get through the progression. Even though it's a progression, it starts with properties of matter, and it moves up to atomic molecular theory. And I'm going to say a little bit more about why I believe that's a major obstacle. It's not a stepping stone, it's a stumbling block. But so that's the paper that was written for assessment.
Yes, right? They wrote it 100% for assessment. How can we test at each grade level what the minimum proficiency should be for the students? And it's important to note that Carol Smith and her team, the author of that paper, are cognitive psychologists. They're not scientists. They're psychologists. Cognitive science. So then now we have to tell me about the NGSS. Where did that in the sequence of things? Yeah, so that's 2006. Then 2007, they write a book. Same National Academies funded, all the things. Okay. Right. And then from there, and then everybody is like 2008, there's this thing on assessment, 2009. Now everybody in 2000 is getting together. Right. Right. And that's really where all of the science standards that are required for your kids in your public school today started and got funded. We got together in June at the LEAPS conference in Iowa, right? And we just get this because we did all the research and figured out. We know what are these people doing? Do this, right? What does high quality zero mean? And this is the long story, the complicated story of what that means. Okay. So. And it took a long time to do all this research and to figure it all out. So, yeah, taking science, that kind of set the framework, and then they were able to reference the learning progression, which was able to then reference this. Right. So now this entire evidence. Right. What evidence? Yeah, they've built their own evidence by writing these books that they could then cite in their next papers. Right. Okay, and that's what they did. Right. Okay, so 2009, they get together at this conference. Right. In June, and that's where it was like, boom, full bore on this. Right. Right. The group that funded all of the whole thing for the standards paid $50,000 so they could all get together at the Keck Center in Washington, D.C. And then that was the culmination of the project for that they were working on it for 2006 to 2009. I can't remember the name of that NSTA, and it was the 12. That was just after. Just after. Yeah, I don't remember it either. So in 2009, what they wanted to do was say narrower and deeper. Oh yes. And so that was a big idea. But Carnegie published a paper. The Gates Foundation published on this. Everybody was taught narrow and deeper. In this same time frame, 2008. Right. And they did. They identified that atomic and molecular theory. Yeah, so it's not, I think it's good thinking to think about big ideas. I think atomic molecular theory obviously is one of the major big energy. I mean, there's big ideas in physics, and then there's big ideas in biology. And I don't think it's a bad idea to talk about what are the big ideas that kids should learn, and atomic molecular theory turns out to be pretty central for all the rest of them. But there were like 4 or 5 big ideas. I'm a chemist, so we dove in deep on that one, and that one tends to be the linchpin for all of the others. In other words, it's the one that precipitated the learning progressions for the others, and actually shapes a lot of what kids learn in the classroom when it comes to science. And so then, okay, so now we have this,
document we can't remember now. But then that leads to...
So they all get together, basically culminated, and they talk about, hey, it's okay to teach something that's not accurate as a stepping stone to teach something that's more accurate in the future.
Right.
And they're specifically talking atomic and molecular theory.
Yeah.
So a bunch of cognitive psychologists and a bunch of educators all got together and said, like, we need to have the kids learn these macroscopic properties of matter as a stepping stone. And then they justified it. And then that was okay.
So, and that's the piece where I wanted to find the evidence for this, because I'm actually open to the idea. I believe that younger kids can learn about, and I think we're going to go into that in more detail, and probably not the episode, but later episodes.
Yep.
But I'm okay if somebody comes up and says, hey, you're 100% wrong, to learn properties of matter first as stepping stones to atomic molecular theory. I'm open to that idea. So show me the data. We found one paper. Right. Remember, it was a 2003 paper. Sneer's paper. Earl Smith was on it, too. But Sneer's paper, and I'm like, here it is. Here's the evidence, right? They were supposedly in this paper testing the idea if kids had in the properties of matter, how well do they transition to understanding atomic molecular theory? So I think there were samples. There were two runs for this paper,
right? And
the total number of students was 28.
Yep. And
out of those 28 students, they were able to validate the data for 7 students. And so this is the paper that's referenced as the evidence using properties of matter as a stepping stone.
Yep.
That's talked about. Evidence using properties of matter as a stepping stone for kids learn atomic molecular theory. And it's a sample size of 28, and out of that 28, only 7 are considered valid data. So I was shocked that this is the only paper I could find. It was the only one who actually even attempted this study. And in a lot of papers, they'll say, oh, well, we have this idea, but we need further studies. There should be further studies. Even the 2006 paper is like, this is based off of conjecture, hypothetical. Yeah. And, there could be alternative learning progressions, and we would need to do those studies. Well,
it's like they said it. It don't matter.
It don't matter. Right?
It doesn't matter.
Right. So we couldn't find any of these papers. There's a lot of papers on misconceptions and cognitive change theory, which we will talk a little bit more about. But there is no other paper that I could find that shows that if you teach students, if students have a good, solid understanding of the properties of matter, that they will therefore have an easier time and fewer misconceptions about atomic molecular theory. It's simply not true. And yet this is cited as evidence in the big 2023 handbook
completely. Oh my God, these guys are really, come on, guy. Like, I'm not going to say the name right now. Dang, I mean, you're just going to not even acknowledge anybody's alternative view or anything that's counter to this macroscopic
first
approach.
And there were. So in the LEAPS conference, that was what, 2009?
2009.
In the LEAPS conference, there was a researcher that did propose learning progression for learning about atomic molecular theory that starts with atoms first, and which I did on my own back in the day, not understanding any of this thing. As just a scientist, I'm like, well, if you're going to teach atomic molecular theory or science, you want to start with atoms. And so that's the way I built my curriculum. I didn't understand that was going to be so controversial. So, okay, so we have the
it was called the Anchors Project.
The Anchors Project.
It was 2006 is when they started it. Eberly from the NSTA drove it. And then in 2009, I'm going to just read you this because I pulled the documents. Let me just read this.
Okay.
It says, in some cases, it is necessary to go from an initial idea to a more advanced idea that is not, but is a stepping stone to the target core idea. For example, the Bohr model of the atom is not accurate, but it is useful to teach as a stepping stone to a more complex model that will be later.
Right. And so, and they also, there's another one in there about mass and weight. I don't know if it's in that one, but that these guys were like, we can mass and weight are not the same, by the way, but in the elementary grades they're taught as if they are the same. And we're going to talk a little bit more about how this builds misconceptions. But in the book, The Map We Never Got, we have a section on the models of the atom. And so what they're saying is not 100% inaccurate. There are different models of the atom that people used over, the century. And the model tells a different story about it represents a slightly different feature of atoms, right? Bohr model is useful, can be useful, but it's only useful in the context of understanding that there's all different kinds of models. When we think, kids learn that there's a model airplane or a model boat or a model car.
Right.
And kids can understand that the model is a full car or a full boat or full airplane, but it tells us something about how they operate, right? Well, it's the same is true with atomic models. So we don't want to teach the wrong information. We want to put it in context. The model is in here. It's useful for certain things. Schrodinger's wave model is also useful for different ways. So the idea that they say we can teach something wrong as a stepping stone, and we're going to clean it up later, right?
That's like, oh my gosh, it's like, hey, let's learn the piano, but let's not learn any of the for the keys.
Or the notes.
Right. Or what is tempo?
Harmony,
anything.
Right?
Right. Let's just teach you something that's not accurate. We'll teach you the real way to do it.
Right.
And that's how it's happening in science education in America today.
Well, and that's kind of leads us to the NGSS and the other piece that we uncovered as we were doing this research. A little bit of the thing that, it's a topic that I was interested in when I was in graduate school for my master's in curriculum and instructional design. And that is this whole idea of So are basically ideas that you uptake somehow, somewhere that aren't true, right, or aren't accurate. And there's a whole bunch of papers around misconceptions and cognitive change, and many of those papers are really good, and there's a lot of evidence that students reach high school full of misconceptions, and these high school kids with these misconceptions have trouble in college. And so you have to have the ideas is that kids are going to develop these misconceptions. One of the misconceptions that students will walk with is that atoms are colored, all right, or that the atoms. So they learn about parts of matter. They learn about the fact that when they call it particles, right? Particles make up all of matter, and then they learn about atoms late middle school and high school. And one of the misconceptions that carries forward is that the particles themselves are colored. And that's one of the things you have to somehow reverse in college, okay? Right. So there's a whole body of research around misconceptions.
Sure. And I think that they used a lot of that misconception research. So basically, in my understanding, I'm not a scientist, I'm just science assistant Dave. And in my estimation, they tested these high schoolers and middle schoolers and asked them questions about atomic and molecular theory,
right,
concepts from an atomic lens.
Right.
And then the kids didn't understand it. They didn't get it. And so they have these misconceptions. But these same people not once gave the opportunity or taught the kids that they were testing these misconceptions. They never once tested them on atomic. Let them learn about what an atom is, not a particle too small to be seen. Teach them atomic theory from the very foundations and up.
Well, and in fact, that's interesting that you bring that up, because remember, Weiser's paper is all about, and they did study, and they're like I said, this is solid research. I don't have any problems with the research. I have problems with the extrapolation that, because based off of these misconceptions, the idea is that younger kids can't learn about atoms and molecules, and we'll talk a little bit more about that as well. But in her research, how does she?
Well, she's doing heat and temperature. She talks.
Well, no, but the one about Yes, heat and temperature.
Yeah, she talks about we could potentially just teach them the molecular kinetic energy differences or the increase.
So yeah, the fix for the misconceptions is to teach kids atomic molecular theory.
Yep.
That's what she writes in that paper. And the challenge, of course, is that most of the time across most schools, and now,
oh yeah,
younger students are not taught atomic molecular theory. This that then got transferred into the learning progression that was published, that then transferred into
because they took all the things. So they had that meeting.
Okay.
And then the Anchors project, they had the meeting in September.
Right.
And by then the whole was on board.
Right.
Okay, so they had picked out who was going to be the leaders, who were going to be the section chiefs, and then who were going to be their lieutenants, right? Like they figured out who the teams were going to be.
Primarily cognitive psychologists and educators.
Yep.
I think there's a couple token scientists on NGSS.
I mean, of course, the first couple of them at the, but if you don't think cells matter and you don't think the kids should learn about cells, then you shouldn't be in charge of the framework for K-12 education. You should not be the person who.
You got very upset when you heard that.
Well, and it's like these kids don't even need to learn about cells, and they're not going to. And actually, cells out of this of what the kids are going to learn.
Right.
So they don't even learn about cells anymore. In the framework for K-12 education, doesn't think that your kids need to learn about cells. Okay. That's really good information.
Well, in order to learn about cells, you got to teach about atoms and molecules.
Well, you do, right? You can't tell them about cells unless you teach them molecules.
Okay, so let's get to the NGSS. So, they had
and then December 3rd, they spent another $2 million. So the organization that funded it spent $6 million in a matter of 7 days, funded the framework for K-12 education, funded the next generation science standards in 2009.
Right.
Yes, a lot of people don't know that. They think the standards came about from the framework. They even talk in their literature, and I read it, I don't know where, but I don't want to quote me on that one. But basically, they knew that they had to have a framework document so they could then create a standards from it, so it wouldn't have the illusion that it was a state-sponsored curriculum.
Right. So the framework book was created essentially at the same time the NGSS was being created.
They were paid 6 days apart.
They did release the framework book first.
They did.
And then they waited and released the NGSS standards later.
They did.
And so backing all the way up, what this means is that the NGSS is built off of this first sort of this big map. And it got funded and pushed through. And there were a lot of people who pushed back on this, and all of those voices kind of got killed.
Yep.
There isn't anything about alternative learning progressions in the Handbook for Science Education
2023. Yep.
The LEAPS conference doesn't really publish the one paper that was
who was the
Swarte. Yeah, she had a paper with an alternative learning progression starting with atoms first. And, by the way, a lot of our competitors internationally, other countries, don't stick to this rigid. The summary of the story is we actually couldn't find any for the NGSS, the way that it's put together, and the high quality curricular material that's based off of NGSS and alignment, supposedly evidence-based. We couldn't find any of that evidence other than that one paper from SNEER in 2003 that we wouldn't consider evidence. Now, they do use a lot of misconception research to justify not teaching students atomic molecular theory.
Well, obviously these middle and high schoolers can't get this information, or they don't understand the atomic molecular theory. So there's no way we could teach younger kids this.
Right. And we can switch gears and talk about, one of the things that I cover in the map we never got. So this book covers not all of this discussion about specifically the standards, but when I look at this, there's a couple of things that stand out to me. So here's the thing that if you take a look, basically what the standards do based off of this Project 2061 document is it starts with the properties of matter. So let's go a little bit into that, because I think this is important. Now that we've talked about each one of these one of the things that stands out to me is that if you look at this K-12 or the 3-5 or the 6-8 band, right? So this is specifically atoms and molecules. Each one is a different topic. This one is conservation of matter. You can see there's a number of different topics. And looking at these overlap, a number of different topics. And if you go further and further into the laws of motion, it's a number of different topics. Now, if you were to pool all those topics together, it's just a bunch of random facts. That's all it is. It's a whole band of random facts that they're introducing to kids. So one of the things that happens when I read this, so I have my doctorate in biophysical chemistry.
Yep.
So, but one of the things that came out of this for me was the idea that, well, hang on a second. What if the curricular material itself is introducing these misconceptions and then solidifying them? So that is the research that we uncovered. That
for their evidence based.
Right. We could not, at the end, there's no connection between, I was actually going to be an oceanographer, but I get really horribly seasick. So I decided not to be an oceanographer, but I ended up getting a PhD in chemistry. And then I was not an educator. I didn't get involved in education until my kids were little. And I just noticed that the textbooks for elementary and middle school students, independent of the publisher, was very lean on actual real science. And so that's why I wrote my real science, introducing them in grades K2 or 3-5, and then they get solidified in 6-8. So by the time they get to high school, they have all of these major misconceptions. It actually takes cognitive energy, a lot of cognitive work to undo. And I'm not going to go into a lot of detail, but the neuroscience behind misconceptions is really interesting. Because once you form a misconception, I mean, they make connections above grade levels for specific subjects, but there's no connections between chemistry. It's not like your brain erases it. What your brain in physics, right? They don't make those lateral connections between the subjects much. And so the other thing that's interesting to me, actively suppresses it and then replaces it with the new information. And I can give you a personal gym on the other side. And as I ride my bike past in my brain, I go, oh, that's pilate. I'm a big reader, but I don't always know how things are pronounced, primarily because I was a whole language learning child. And so I never learned phonics. So I struggle with pronunciation sometimes. It's Pilates. It's Pilates. And so that's the nature of misconceptions. Once you have a misconception, it actually takes way more cognitive to not necessarily undo the misconception, but to kind of, I can see, so thesis of this map, of the map we never got. So one of the things that the conclusion that I came to after we did all this research.
Right. And spent 9 months driving around the United States.
Right.
In our RS4K atomic.
Right. Doing the Atomic Roadshow. We had a blast doing that. We were able to teach a lot of kids about atoms and molecules, even down to suppress it and then replace it with the correct conception. Okay. As I looked through this, there are a couple of things that I can see where the misconception starts. So one of the misconceptions that students have is that gases are not made of atoms or molecules. Okay, gases are. But I saw the word Pilates written before I heard its pronunciation. So in my mind, it's pilates, because that's the way I pronounced it when I read it. The first time I read it, it was a pilate. This K2, this is the K2 band for states of matter. This is what the topic says. It says water left in an open container disappears, but water in a closed container does not disappear. So think about unpacking that. Water disappears. It just goes away according to this topic band here. That's what they're going to teach us K2 student. Water disappears. Okay? Okay, kids to just do it over a summer. And you can just trace the misconceptions along through, because we all have misconceptions, and the reason we do is because of the way we were taught science. So this explains now more clearly why we see this dip.
Yep.
And why we see fewer and fewer kids going into STEM careers. And actually, many universities have to do remedial classes.
And they're everything.
Well, and I think it is also worth saying that all the incumbent curriculum materials are written off of this.
Yep.
And most STEM products are also formulated off this. Now, there are some exceptions. We're an exception. There's a few exceptions. I list some curriculum materials in the back of this book that